You're welcome. Presenting our president, Jessica Miller.
I'm sorry if you hear car noises in the back. I'm at work at the track. My announcements will be short. Welcome to this month's lecture. We, as Linda mentioned, we are having our 70th anniversary next year, the SFA, and we are currently collecting images or stories, anything that can be digitized. If you have any in your archives, if you have any pictures from star parties or from events or from lectures, or if you have any historic memorabilia that can be scanned and digitized, we would, and you'd be willing to share it with us, we'd love that. If you can email it to images@sfa-astronomy.org, or to myself, which is president@sfa-astronomy.org. And if you could also include the information about the photo, who's in the photo, if you know it, and about when it was and date-wise, and then what it is, that would be great. And our board member that handles our telescope loaner program is spearheading collecting all of the photos and gathering all of that info for next year. And we are currently planning some events for next year, which should be very fun. And we will get, as soon as those events have been finalized, we will let all of our members know. But that is all of it for the president's announcements tonight. And I'll hand over to Linda.
Okay. Hello, this is Linda Mahan. I'm going to introduce the next 2 months upcoming lectures. We always meet on third Wednesday, and this is for October the 20th. And we meet at 7 o'clock on Zoom. Living with a Star, the Sun, Space Weather, and Our Place in the Solar Neighborhood. This is given by Dr. Phyllis Whittlesey, UC Berkeley, the Space Sciences Laboratory. As humanity expands its presence on the moon and Mars, we will venture outside of Earth's protective magnetic bubble. And on Earth, we will also feel the effects of space weather. Several currently operating and future NASA and ESA missions need to uncover persisting mysteries about our sun. Dr. Whittlesey is an instrument lead for an instrument aboard the Parker Solar Probe, which was launched in 2018. And she's currently also leading instrumentation on 2 of NASA's Heliospherics Division's missions that are currently in development. November the 17th, Dr. Gabor Basri, Emeritus Professor, Astronomy, UC Berkeley. His talk is A Star is Born, and Planets Too. We'll learn how newborn planets prepare for the birth, how newborn stars prepare for the birth of planets. And we now live at a privileged time when we can see this development. This presentation will be richly illustrated with images from major observatories on Earth and in space. These have enabled us, along with computer modeling, to learn how stars and planets are born. And we will watch the whole process unfolding. So please join us in October and November. And now we'll also talk about our speaker. After earning her Bachelor of Science in Physics and a mathematics minor from Cal Poly San Luis Obispo, Marita Beard worked as an assistant scientist in astrophysics research as a contractor at NASA Ames Research Center, Moffett Field, and then in education and public outreach, developing science curriculum through the SETI Institute. The desire to work directly with students and the opportunity to inspire more young women and students of color to STEM education has led her to a teaching career at Campbell Union High School District in 2005. She currently teaches physics and AP physics at Lee High School in San Jose. Please welcome Marita Beard as she will take us to shooting stars on the stratosphere with the Sofia mission. Welcome. We are looking forward to your presentation, Marita.
Thank you, Linda. I'm so happy to be here with all of you. Thank you so much for inviting me. It's been a long time since I've had to gotten the opportunity to talk about Sofia to the general public. I talk about Sofia with my students all the time. So I will just take you a little bit, sort of share with you my journey, what I know about Sofia, what Sofia is, what exciting science Sofia has published already for the scientific community, and how my Sofia experience has impacted my teaching. So let me click here. Sorry. There you go. So I just repeated the slide. I wouldn't go ahead. So my journey from when I started to today, a bit about Sofia and infrared astronomy, the Airborne Astronomy program, Ambassador program. I call it the flight franchise. I'm one of the few people who have had teachers who've had the opportunity to fly on Sofia 4 times. And then what life has been like after Sofia. And then I'll have some time for questions. So let me tell you a little bit about myself. That's me on the left-hand side. And then my mom and I think one of our first ventures here to California, I'm originally from Guam. My ethnic background is Chamorro. So that's what you call the people from Guam. So when I look up Chamorro people in STEM, there aren't a whole lot of us. So I didn't have a lot of role models, except for my mother, who majored in biology at Canisius College. She was well on her way to a pre-med sort of career. And then she got pregnant with me, moved back to the island, and married my father, and pursued a career in medicine, but not as a doctor. She's a neurodiagnostic technologist. So my desire to pursue a STEM career came from the models, the examples that my mom set for me, as well as, these are my parents. My grandmother here, I'm gonna do a little quick annotation because I'm savvy with that from distance learning. I just wanna circle my grandmother here. Her name is Guadalupe Sablon. My grandmother was born in 1913, or I'm forgetting now, but early 1900s. And she lived through both world wars. She lived with us for a long time. I'd say when I was a teenager, she spent a couple years with us, and she'd tell me all the stories. And she would tell me all about how she had to quit school after 6th grade. She loved school. She loved English. She especially loved math. But in those times, children had, especially the girls, had to leave school so they could go work and earn money for the family. And so she always impressed upon me how important education was, how much she loved math and science, and how she wishes she had the opportunities that I had growing up. And so she also inspired me to pursue a career in STEM. I'm going to clear that little circle now. Sorry here, just lost my mouse. Uh-oh, sorry here, folks. Little technical difficulties here. We get to the okay. Sorry, my mouse has since disappeared, and I'm just trying to get rid of that. Enter. Oops. Can you guys hear me? Things are like sort of freezing up here. Oh, here we go. I got it. Sorry. My apologies.
Yep. We hear you fine, and we've seen everything so far.
Okay.
All's well.
Okay, I just gotta try to get out of this, try to be fancy here. I did distance learning all year long. Let me see here, why is it not? Oh, okay. I'm sorry, folks, I'm just trying to get rid of this here, and it won't let me advance. Let me see if I can temporarily sharing, and oh goodness. Okay, I'm not going to try to be fancy again, but let me just see if I can't reset here.
Okay, we are still looking at your family photos.
Yes, I know. It won't let me get out of this here. Let's see here. I'm gonna see if it'll let me. Okay. Oh my dear. Clear that. Oh, let's see here. Let's see what's going on.
Do you want me to maybe?
Yeah,
I can stop your sharing, and then we can restart it.
Thank you, Jay. That would be really wonderful. Thank you. Yes. Okay, let me try that again. There we go. Thank you so much. All right.
Okay, we're back.
Continuing the story about women in STEM and minority women in STEM, I went to Cal Poly San Luis Obispo. I majored in physics and minor in math. As you can see here, I circled myself. There's only one other person who's a woman in this course. This was a advanced physics course. It was electrodynamics. So I'm circled and there's one other. So I felt kind of alone in my physics classes. And so I've always thought that's something wrong. There was something wrong with that. And so I love math and science, and I also loved school. And so I knew that at some point in my life, I would go into the classroom and hopefully inspire young women and students of color into a career in STEM. And I also worked on the Navajo Reservation as part of my college work experience, where I worked as a student teacher, working with Native American students transitioning from high school to college. And this is just a little bit of my experience here. It's just, I've always wanted to be a teacher. And then right out of college, I actually worked at NASA Ames in astrophysics branch, working for the Aries instrument team, which stands for Airborne Infrared Astronomy Grading Spectrometer. And this was an instrument that was originally awarded to be one of the instruments on Sofia. So that's how I knew about Sofia from my work at NASA Ames. And this is my leaving Sofia team to go into teaching at this point. My original goal was I'd go work at NASA, go fly on Sofia as member of a research team, then eventually get my teaching credential, and then maybe someday be an educator on Sofia. Well, this picture was taken back in 2000. Sofia did not start flying until 2011. So I couldn't wait for Sofia to fly to get into the classroom. So I did do some education and public outreach with the SETI Institute, developing curriculum. Here I'm demonstrating to teachers in a workshop how to model a comet. And then these are the current people who inspire me to continue inspiring children of color and young women into STEM. My son Sam and my daughter Marissa. That's when I first started Sofia. This is how old they were. This is how old they are now. I'd love to say that both of my children are into STEM. My daughter is very much not into STEM, but she is a smart young woman and is wanting to pursue a career in music. My son is definitely a STEM person. He wants to pursue a career in nuclear energy. And my husband, I like to call us a nerd family. Since I have a physics degree, my husband is a mechanical engineer. He works at NASA Ames Research Center in the flight simulations branch. So there's a little bit about my family. As Linda stated earlier, I do have a minor in math from Cal Poly San Luis Obispo. I majored in physics. I also got my teaching credential at San Jose State. I first started teaching at Branham High School, which is also in the same district in San Jose. And then I went on to transfer to Lee High School, where I now teach physics full time. I used to teach earth science as well, which is where I got to share my passion for geology and astronomy. And so these are some of my students from Branham. I really am a firm believer in the Cal Poly's mission statement, learn by doing, and I do the same thing in my classroom. And so these are some of my students way back when I taught at Branham. I still do the same project. They had to build a pumpkin chunkin trebuchet. And so this is on a soccer field. They were launching pumpkins. And then this is now Lee High School. This was pre-pandemic. So this was fall of 2019. This was our all physics students at Lee build a pumpkin chunkin trebuchet. True story. And I will not name names, but there was an administrator, past administrator, no longer in the district, who was worried that there would be pumpkins growing on the front lawn if we started launching pumpkins on there. A side note, when I had to ask permission from the facilities people if we were allowed to launch pumpkins, they said, sure, as long as if any pumpkins show up on the lawn, I make them a pumpkin pie. So there is one of my projects. I also took students years ago indoor skydiving. We did that for fun. But also I have students design and build a boat out of cardboard that they have to row across the pool in a race. And the only prize is their picture on my wall of fame, but they love it. And it's one of the biggest hits. It's the highlights, I've been told, of their high school science career are the physics projects that I brought to Lee. So let's talk a little bit. What we're all here for is astronomy. And this is what I tell my students, because students think that like everything we teach them in our classes is like, everything's been discovered. And no, it hasn't. These are questions astronomers are still trying to answer. What is the future of the universe as we know it? exactly how big and how old is the universe, what makes up the universe and how is it organized, how are stars and galaxies formed. I heard Linda say that one of your next guest speakers are going to talk about the birth of a star. So I'll definitely have to join you on that one. That sounds super exciting. Where else might we find life in the universe? And the biggest question that lots of students try to answer, not just astronomers, is are we alone? And how do we answer those questions? How do astronomers try to answer those questions? Well, they collect light. The light is not just what we see with our eyes. It's also light we can't see. So I talk to my students about the entire electromagnetic spectrum, everything from gamma rays to radio waves, and that it's the light that tells us information about stars and planets and galaxies and other cosmic objects that astronomers are interested in studying. And so temperature is one of the things that determines the main type of radiation emitted. This is a graphic that I share with my students. And it's basically the different space-based telescopes, what wavelengths of light that they're interested in collecting and studying. And that there are different types of observatories. There are ground-based observatories, such as in San Jose, we talk about the Lick Observatory on the top of Mount Hamilton. This is an image of the HST, Hubble Space Telescope. And then I had to squeeze in, of course, this is a picture of Sofia in the air. And Sofia is an airborne observatory. Sofia is not the first airborne observatory. Back in the late 60s, early 70s, there was a Learjet that they put in a 6-inch telescope to collect infrared light as well. The successor to the Learjet was the KAO. Maybe some of you who are infrared astronomy buffs might have heard of it. Stands for Kuiper Airborne Observatory. I'm sorry, I don't remember the specs on that telescope, but I joined the astrophysics branch at NASA Ames 6 months after the KAO was retired, and came in when the Sofia was being proposed by NASA astronomers there. So this is just an image that I share with my students. Like, this is a composite image that astronomers can create, but this is an image of the Pinwheel galaxy in X-ray, optical, and infrared. What's even more eye-opening for students is to look at, I hope everyone, my favorite, but Orion. So this is what Orion, because they can recognize that constellation in the night sky. Most students can. And if they can't, we talk about where they could find it. So on the left hand is Orion, what you can see with visual wavelengths, kind of sort of like with your naked eye. And then if we look at Orion with through an infrared filter or an infrared telescope, you can see that there's so much more going on that we cannot see, and that we're looking at the heat signatures of what's going on there. And so we talk about Orion's belt here being a hotbed of star formation. And then we talk about the different types of stars, Betelgeuse, and I know you guys are probably better at naming the stars on the constellation. I just remember Betelgeuse. Okay, so here's the challenges for infrared astronomy, though, is that the water vapor that makes up our atmosphere tends to absorb almost all of the incoming radiation. So even mountaintop observatories like Mauna Kea, the Keck Observatory in Mauna Kea, and the Lick Observatory here in San Jose, they get a limited view of the infrared universe. So we wanted to try to get those wavelengths, but as you can see in this graphic here, much of the infrared light is absorbed by atmosphere and does not transmit through. And so how can we get that information? The option was a space-based telescopes. There's some limitations to space-based telescopes. Space-based telescopes, you build them, you put them up in space, and pretty much you're stuck with the technology that existed when you built those space-based telescopes. The advantage of an infrared, oops, sorry, I forgot about talking about what happens there. So this is energy from the sun, gets absorbed, some of it radiates back out. There we go. Where we put our instruments, and so this is where we can put our space-based telescopes and ground-based observatories, but there's still an area that an airborne observatory can tap into, ground-based telescopes, and that space-based telescopes, as technology evolves, are, we're sort of out of luck if it breaks, although we're lucky that Hubble Space Telescope has lasted as long as it has. But that's the advantages of VIA. So that's what, and this is just a cool image of the stratosphere. This is where Sofia flies in the stratosphere above the vapor. Another advantage of a Sofia is that it has a 100-inch telescope, which has better clarity, sharper imagery. And so the answer to those obstacles with infrared astronomy is Sofia. And so I kind of jumped ahead of myself here. So there are 3 parts to Sofia. It's a 747, Boeing 747 SP. The SP stands for special performance. What's so special about its performance is that it can actually reach altitudes a lot quicker than other 747s. So it reaches altitude pretty quickly because you do not want to waste fuel and time on just trying to reach altitude. You want to get to the altitude that astronomers want to get to the altitude that they're above the water vapor so they can start collecting data. And it needs to be able to fly for 10 to 12-hour missions. It's got a ginormous telescope, well, not ginormous, a 17 metric ton reflected telescope that can, be able to point precisely at targets in the universe. I'm going to show you how a telescope is able to latch on to a target and not be, and still get good imagery. I don't know about you, but when I break out my telescope, I point it at the star, and then the next thing you know, I have to like realign it because the star is moved out of focus of view if I walk away. The other advantage of Sofia is that, as I mentioned earlier, is that you can change out the instruments as technology evolves. This is just an image of the aircraft. This is the telescope. On the back there where you see the bulge there, it's a dark area. That's where the telescope sits. This is an opportunity to see the telescope on the ground with it open. They don't do that very often, right? We want to keep the mirror very clean. So this is the primary mirror that you are looking at. It was a rare opportunity after my first flight where we got to tour. It was a big press junket sort of thing. And so we got to tour, and then I snuck my opportunity to take a picture. I don't think I'm supposed to take the, I did. And so here's a picture of the telescope a little bit more. This is what is exposed to the elements. This is how it looks inside the cabin. And so showing you the light path here. Just pop up in a second. There we go. The light hits the mirror, hits the primary mirror, and then is reflected up to a secondary mirror, and then down to a tertiary mirror, and then down what's called the Nasmyth tube. And then on the bottom right, where it's inside the cabin, you see a yellow arrow pointing out of the middle here. That's the Nasmyth tube. And that's where scientists sort of like hook in their instruments. So, and then this is just another animation of the light pathway. So I'm gonna let it animate the same thing. So here we go. It's there's light from the star. It hits the mirrors, reflected through the secondary mirror. And then there is a second mirror that allows to reflect visible light, because there is a visible light capability. There's a camera there so that they can check that they're pointing in the right area as well. And then, so here's a picture of me inside there. So when my first flight, the instrument was Forecast, which is from Cornell. And so I'm standing right in front of where the Nasmyth tube is. It looks sort of like you can see sort of this sort of big ring around it. That's the pressure bulkhead. And the really amazing engineering feats that they came up with is that, you know, the plane's going to be jostling around due to turbulence. How do you keep that telescope pointed and tracking that star? What it is that the telescope mounting is on, I want to say, just a couple microns of oil that allow the telescope to sort of jostle around, much like the yolk in an egg, right? The yolk in an egg will have to stay in the center mass of that. You can roll the egg and the yolk sort of same thing. So really what's happening is that our telescope is pointed at the target object, and the plane is like the egg whites jostling around all around the telescope. The telescope stays pointed at the same object. And so this is what an inside diagram of the inside cabin here. So there's that's where all the scientists, guest scientists, principal investigators sit. This is a 747 that has a second level. So the top level, there's a staircase you might see there next to the main pressurized cabin label. That staircase leads up to where the cockpit is, and I guess in commercial air flight days, that's where the first class people sat. Towards the back by the staircase, you'll see two consoles to the right of the red staircase. I don't know if you can see my mouse pointing, but that's where the educators sit. So there's a table. It looks like there's like a little conference table, and right below the conference table is some computer consoles and 3 chairs. That's where airborne ambassadors like myself were able to sit during. We can get up and walk and move forward, or I guess backwards, towards the investigators and the telescope operators and the guest scientists and talk to them. But that's where we got to sit on takeoff. Okay, so these are just some more images of the inside of Sofia. So the first one was just, you could see the telescope and the instrument. And then this picture that just showed up, that is where the telescope operators sit. And they're the ones that are in charge of the plan for what they're going to observe. And then this is a view of where the educators sat. And so there's the 3 chairs there. So that's where I got to sit. We get to see exactly what the telescope operators see, but we controlled nothing. And then this is just, this is that conference table that you saw it was pointing to. So at times we could just meet with some of the guest lecturers, with the guest scientists who weren't actively collecting data, and I could interview them and ask them about their career pathway so that I could share it. Because that's what my main focus was, is to share career pathways with my students so they could see that you don't have to have a PhD to be a part of the Sofia project. So I kind of went over these details already, but it's just a comparison of Sofia versus the Spitzer infrared telescope, right? So Sofia's mirror is 3 times bigger. So that means that it can see 3 times smaller details, 9 times the resolving power. And then it has can analyze a wider range of infrared wavelengths. And then I think the real big selling point was that you can have 2nd, 3rd, and 4th generation instruments as technology evolves. Remember, I was a part of Sofia in its initial proposal process back in the early 2000s. And as we all know, technology has evolved so much since the early 2000s, right? We have cell phones that can do amazing things and are a lot smaller than they were in the 2000s. And that Sofia also has a design lifetime of 20 years versus Spitzer, which is supposed to be only 5 years because it's limited by the cryogen supply. So Sofia is a lot more flexible as an airborne observatory. There we go. And so these are some of the Sofia's areas of science, areas of interest in science. So when I was on Sofia, the astronomers that were the principal investigators on there was interested in mapping out the galactic center. I talked to my students about how scientists astronomers say that there's a black hole at the center of every galaxy. And so that when we were on that those scientists were looking at the structure of the center of our galaxy. They're also interested in studying the interstellar medium, formations of stars and planets, and also planetary science. So that's the main 4 areas of Sofia's interests, but doesn't mean that's all they did. And I have some highlights of recent science headlines. So what has Sofia done in its 10 years, by the way, 10 years since my flight. And first flight for Sofia was 2010. And so I flew in 2011. So they have discovered the first type of molecule known as the helium hydride. Sofia also discovered that stellar winds from a newborn star prevent any, I called it star sisters because I like alliteration, because of when that newborn star forms, it creates its own sort of shock wave throughout the nebula and prevents stars nearby forming. Sofia has also discovered a nearby planetary system like our own. And then one of the flight that I was on contributed to this images of the galactic center that reveal the birth of massive stars. And so those are some of the science headlines. And the biggest headline was the one that was released, I believe that was just last summer, right? I think I want to say 2020. I believe that, or is it 2021? Oh my gosh, the years are melting together. But Sofia, their research discovered water on the sunlit surface of the moon. You can go to Sofia's website. You can just Google Sofia, NASA Sofia, SOFIA, and they have a science page to tell all of the details about the science. So I actually advertised to my students about this last year. maybe it was last summer. I'm sorry, I forget what year this was. Okay, and so then these are the first generation science instruments. Were HIPPO. It looked at ultraviolet, visual, and near infrared. Then there was Flight Cam, which is a near infrared camera. GREAT was a far infrared spectrometer, and Forecast was a mid infrared camera. Now, I don't know if you remember me saying that I was part of the Aries instrument team. Now, why is Aries not on this list of instruments? Is it was too big to fit onto the plane. When all was said and done, wasn't gonna be able to fit, and so Aries was scrapped, and then these are the 4 that were chosen. And so Sofia, this is an old slide, sorry. So Sofia takes teachers up into the plane. It's mostly like a ride along, where you get to see, be on a flight, a mission where astronomers are collecting data. We're allowed to interact with astronomers, ask them questions, interact with the flight crew, pilots, telescope operators, and even grad students that are there, working on their PhD, helping out their advisor. And so this is Sofia, a picture that is not my own. This is I got from Sofia's website. But this is Teresa Paulson. She was my partner. We were the second set of teachers. So we were about the third and fourth teachers to fly on Sofia. We lovingly call ourselves the Sofia 6. That was the 6 teachers on the whole country were selected to fly that first year. It was an amazing opportunity. We all bonded. It was sort of a landmark sort of thing because Sofia, was 10 years past due, and they really wanted to get teachers on. So Teresa is from Wisconsin, and we had teachers in Washington, D.C. We're fortunate that they were able to select 2 teachers from California, myself, and then Kathleen Fredette, who is on here somewhere, one of these here. Oh, you can't see her here. So she's from Palmdale. So these are the Sofia 6. And then also Sofia is a collaboration with DLR, which is Germany's space agency. And so they also fly at least 2 German teachers that year. So the first year of flight was 2 German teachers. So these are the Sofia 6 plus the 2 German teachers. Sofia the one benefit is that you can fly anywhere in the world. Sofia is deployed to Christchurch, New Zealand, to look at the southern skies. I keep asking them, you can take me on that mission, and I'll gladly fly to New Zealand to be a part of that. And so this is what it was like. So I just want to share some pictures from the different flights. So the whole process for me was, there is the security guard where you have to have the special badge to get on. It used to be called Dryden Air Force. It's now Armstrong Research Center. And then this is the egress training. In the beginning, everyone said, are you afraid to go on Sofia? And I knew it was an airplane. But then once we had these egress training, in the event that something happens to the plane, you have to be able, when it's upside down, to slide down this big slide. And I don't like roller coasters, so I definitely don't want to have to slide down a big slide at the top of an upside down plane. But this gentleman here that I'm sitting next to, he was showing us how to escape the plane. This is Dr. Eric Bleckland from UCLA. He was one of the principal scientists on Sofia. And then these are 2 former Sofia managers, Eddie Zavala, and I'm forgetting the name of the guy on the far right. I feel like his first name is Charles, but I can't remember his last name. I apologize for not remembering. And then we had a videographer tailing us because they wanted to document this. And then this is Coral Clark. She works for USRA, University Space Research Association, and she was our liaison, sort of our escort throughout the process. And this is us right before we get on the plane. And then we got to tour the cockpit. So I thought that was pretty fun. That's the only time I've ever been in the pilot seat of an airplane. And then I'm pointing this because I am a science nerd. And Bill Nye, the science guy, also got to tour Sofia before I did. And so he he's the only person that's been able to autograph the Sofia walls there. So his name is there in perpetuity. This is a photograph I took just sitting in my seat from the airplane on our first flight. And then they actually do have a safety information card. They made it special for Sofia, so I'm sort of modeling that, mostly to show my students that, you know, there was a graphic artist and a writer who designed the safety information card. So maybe you don't want to be part of the flight mission, but you can help produce materials that are on the airplane. This was our flight path on my very first flight. And so the black area is we start here, and on the bottom left corner is where NASA Dryden or Armstrong is now. And then we follow this path, and you can see that we go all the way out to, we went as far east as, I want to say, Kentucky, right? It looks like and then we did a little loop and then went backtracked. And then we went as far north as southern Idaho, and then back down and around. We passed over Las Vegas. So this was the flight path that we took on my very first voyage. So that was June 4th was the flight that I took. And then this is just an image that I took, have of forecast. That was the instrument that was on Sofia when I flew my very first flight. And this is me and Teresa again. So my current students would say boo because there's a rivalry between Branham and Lee. But this is my first flight here. And this is right there behind us. That's where the principal investigator. So we got to get really up close and talking with them. This is probably a picture from my second flight, sitting there. That second flight was more like I think it was, I don't remember the science that we did, but there was another, it was supposed to be a filming for Mighty Planes, some Discovery Channel program. I don't end up being on that plane video, they cut me out. But this is going back to our flight. So this is Dr. Terry Herder. He's the PI for Sofia Forecast. And it was super exciting when it happened, and he was explaining to us how they get this image. But this is the image on the left-hand side is the published image. So this was at the time, so back in 2011, this was the highest resolution image that we had, that astronomers had obtained of the galactic center in the infrared up to that point. And so he was explaining to us the process of chopping, which is subtracting out that background radiation, being able to only focus on the radiation that we're interested in from the actual center of the galaxy, which is what they were interested in studying. So he did a great job and was very patient with us in explaining that whole process. And so this is another image of the galactic center. And then I think this is an earlier published image. And so you can see going back and forth, there's this little swoosh where it says there's arc, an arrow pointing to the arc, and you can see the swoosh. And so that's the another published image that they put out. And then we landed, it was a long flight, so it's at least 10 to 12 hours. That flight we got as high as about 45,000 feet. And we took off right before 7 p.m. and landed right after 5 a.m. I drank a lot of energy drinks to stay up. I've only pulled one all-nighter prior to that, and that was one time in college when I was trying not to fail a world history class because I cared more about my physics classes than my history classes. And so this is just us landing. And then later on, and there's a couple of full circle moments in my life. This is Alan Meyer. He is the telescope operator. And when I worked at NASA Ames with the Ares instrument team, he was one of the people that I worked with. And it was just so coincidental that he was also the telescope operator on the flight that I was on. He's also was a telescope operator on the KAO, the predecessor to Sofia. And then this is just a document that I did fly on the Sofia multiple times. So this is myself, Kathy Fredette, and then Dr. Dana Bachman, who is the Education Public Outreach Manager for Sofia. He was our liaison for this flight. This is probably another flight where, this might be the Mighty Planes flight image. And then I got to fly on Sofia a four times. I was asked if I was interested in applying to go on another Sofia mission, and I had, without hesitation, I said yes. I was supposed to fly in May of 2015. That flight got delayed, and then it was postponed to 2017, and then it got delayed. And I believe that flight finally took place. It was September of 2019, right before the pandemic happened. So I coincidentally was on, this is cycle 5 now. I was cycle 0, and now this is cycle 5 later on. This is 2019. And the gentleman right here was my master teacher when I was working on my teaching credential. That is Brad Bedell, who teaches science at Santa Clara at Wilcox High School. So it was another full circle moment for me coming with a mentor. He was my mentor, and we were both on the same flight. So these are just some more pictures of right before we took off. So the other woman there, Amanda, she and I, we kept getting bumped off of Sofia flights because 2 years prior to that, there was something wrong with the engine. So that's why we didn't fly. So they kept postponing and postponing. They take safety very seriously there. And so this is us on our way onto our flight. And so I got to, this is, since 2011, and this was 2019, there were a lot of changes. And so I got to take pictures of the console. And this is just to show you on the right-hand side that we can see an altitude, temperature is 17 degrees Celsius. It can tell you the altitude. We're only at about 7,000 feet. And so I interjected some images there. So it's still light out. Sun hasn't set yet. We're just trying to, it's almost about to set. Let's see, local time is, well, it says universal time. I think local time was 7:30. So this was a September evening. This was our flight path for my last flight on Sofia, which I guess when I get right, 2018. I'm so wrong with the dates. I'm sorry, 2018 is when it was. Anyway, so this is the same, it's in 2018, it's the same flight path. September 11th, 2018 is when we did this pathway. And so I just took pictures that you can, at the educator console, we get to see what the telescope operator sees. You see this sort of windmill looking-ish item in the middle of the screen there. That shows you how much of the telescope is open. And so eventually that'll be fully opened. I couldn't find an image of it fully opened. And then, so I just take more pictures of the console just so you can see what it's like for educators. Then I got a chance to talk to these grad students who were, they were crunching the data. And then I found this image later. That was a preliminary image, the optical image of what they were looking at. So that's why it's so fuzzy. I'm sure those numbers mean something. I just don't remember exactly what they mean anymore. But I got a chance to talk to this young woman and ask her about her pathway. What's her major? She was majoring in astrophysics, or she was working on her astrophysics doctorate. She was also from Cornell. And then this was about, so let's see here, I don't know what local time is, but 10 UTC. This was a remarkable moment. The image on the right-hand side, I took from the airplane, shot out of my window, and that is the Northern Lights. I almost cried when I saw that because it's always been on my bucket list, and I always thought I would be a retired teacher before I ever saw the Northern Lights. So it was pretty amazing. The pilots called us up and said, hey, you can come see it upstairs. It's going to be a lot clearer. And it was a lot clearer, but I can't like sit in the pilot's lap and take my picture. So I just enjoyed it from behind. But that's what I took out of the little windows that are in the lower cabin. Notice that it's minus 50 degrees Celsius here when it says static air temperature, minus 50 degrees Celsius. It is very cold up there. And this is just some more images of what it looks like. This is the educator's console. So it's like they're showing us the optical, they're showing us the infrared. And I'm sorry, I don't remember what the blue image is for, but I just was like, just happy to be there. And then let's see here, now it's September 14th. So it's past midnight now because it was I guess it's September 14th, yes. And so it's past midnight, and let's see here. The temperature is now minus 60 degrees Celsius. It never got colder than that, thank goodness. But if you look at our altitude, it's 43,000 feet. The actual the stratopause, which is the barrier between the upper troposphere and the stratosphere, it varies because it changes with pressure and temperature, right? And so this flight, we flew at 43,000 feet. My very first flight, we flew about 45,000 feet. I point that out to my students that it's not like a hard number there. And then we landed, I don't remember what time we landed. I just knew it was sunrise. So probably about 6:30 in the morning. And so this is like, yay, I made it. And then I just loved taking pictures of the plane because the plane is a gorgeous, gorgeous plane. And then a little bit about life after Sofia. So in the beginning, back in 2011, I was all over the news. People like recognized me, and my 15 minutes of fame were over until Linda called me. So it was just news. So it was all over the news about that. As I said earlier, I am originally from Guam. And so I got recognized by my congressional representative from Guam on my work. So it was such an honor. Of course, my parents were super proud. And then I was in the local newspaper, the local resident newspaper, a couple of times. This is one from my neighborhood. And then we got to do a sort of like, it's kind of like, I felt like we were rock stars, and we got to do this like tour, Sofia Tour. And so the Sofia 6, we got to go to Yerkes Observatory. And we also got to tour the instrumentation labs. This is the instrumentation lab there. This is Yerkes. Sorry, I'm backwards here. This is the instrumentation lab. I forget what instrument this was. I want to say it's Hippo. And then we all went to, this is all 6 of us. We all went to Yerkes Observatory and shared our experiences with Sofia with some teachers, about 20 teachers there. And then I got to tour, give a talk on Sofia. Sofia came up to Moffett Field and was on public display, and people could tour Sofia. This was back in 2012. Couple years ago, Sofia was up again for a tour. I didn't go on that one, but I got to talk about it and bring my students. So these are my students from Branham. This is 2012, my last year teaching at Branham. And so it really had an impact, so much so, let me try to find a picture of her. It's this girl right here. This girl here, she decided to major in astronomy, and she's an active member of the Astronomical Association down here in the SJAA. So these are more pictures of my students that got to go to Ames and tour. Oh, sorry, this girl here, the wrong person. That's the girl. Sorry. 1,000 faces. It's hard to remember which blonde am I talking about. Okay, so then this is all my students that I was able to bring. I brought all of my physics students and my earth science students. And so it was a nice spectrum so that the younger students could see what Sofia was all about. And then I transferred to Lee, and I constantly talk to my students about Lee, about Sofia. And it's hard to tell because I don't have a really good picture, but in the corner next to the bottom right picture, the door, I have all my Sofia pictures up there. And I refer back to them when I talk to my students about Sofia. Thank you so much for listening to my talk. That's what I have to share with you. And I'm hoping if you have questions for me.
Wonderful, thank you. Anyone in attendance, please feel free to unmute yourself and ask a question, or if you prefer to type into the chat, I will watch there as well. I see Linda is reaching for her button. There, no. There you are, Linda.
Ah, so many questions you answered for us. It was amazing. And my question would have been, how could it possibly be the plane stay stable and not have it jostling around? So the egg metaphor was really, really good. Even if you have vibration pads on tripods on a telescope here on Mount Tam or something like that, a little vibration can take the star or object and make it really move. So having the dynamics of a plane, that was one of my real wonders, is how were they able to stay focused?
Yeah, it's I want to say 3 microns, and it's an oil, 3 microns of this oil. I'm not sure what oil, but yeah, that's how it's able to move around. So yes, thank you. Yeah, no, it's an amazing engineering feat. Yeah. also just building the mirror, just the whole telescope is engineering marvel. You know, the telescope, 100-meter telescope, cutting a hole in the back of the plane. They had to do a lot of they did a lot of the wind tunnel, the tests of the shape of the they call it the garage door where the telescope, the mirror sits in. They did a lot of tests, wind tunnel tests at NASA Ames to figure out what the right shape was so that you wouldn't get that additional turbulence of air moving over the opening where the mirror sits.
Wow.
Are there future missions still planned to
Yes,
take teachers?
yes, they are. There's I just got to notice that there's I want to say it's cycle 9 that's coming up there. They did a call for teachers. Of course, there was a pause for for COVID. So yeah, they're trying to get teachers back up in there. Let's see here. How do they keep the scope on focus when the plane is moving so fast? So they have the telescope operator, like Dr. Meyer that you saw there. He's responsible for making sure that the telescope stays pointed at that object. But it's really like, if you're thinking about it, like I can look up at the moon right now and I can run around my backyard as fast as I can, but I could still keep my eyes focused on the moon. It's the same thing. It's such a far away object that the telescope is able to do that. That's my best, my best answer there.
Yeah, I was thinking the same thing myself. As when you set up your telescope in your backyard, the objects are moving. So eventually they move out of the field of view, and now we have automated telescopes that will adjust for the rotation of the Earth. But when you're in a flying plane, I wonder if they program into the telescope control the path and speed of the airplane, if it's something that is even possible like that.
Yeah.
It's on autopilot and the plane flies around the telescope.
Yes.
So the plane just shakes like crazy. I went to Ames and I saw when it was on the L-1011 instead of the 747. It was a smaller plane back in the 70s, and it was pretty interesting, especially the wind tunnel and all that stuff.
Yeah. Let's see here. We've got a couple questions here. How do teachers apply to fly on Sofia? Is there a selection process? Last I heard, and that's why I got to go on like my 4th flight, is that Sofia is working with agreements with school districts to get multiple teachers, because their goal is to get their reach as many students as possible. Sofia has since their education department has developed curriculum that I've used with my students several times. I did the full curriculum that they came up with, which is talking about filters, talking about the different wavelengths of light, and how astronomers create those beautiful pictures that are on like astronomy picture of the day. How are those images created? And it's a great, wonderful program. So they want to get those out to all the to as many students as possible. So there is usually an agreement. If you are interested in applying to be a teacher, an airborne ambassador, I would be happy to send you the contact person on how to get that process happening. When I first started, it used to be just individual teachers could apply, but in the last 5 years, they've since due to like agreements between districts. It's a memorandum of understanding or something like that. Is it correct that the objective is to take a picture of space objects as opposed to direct observation? The objective is to, well, when we're looking at infrared light, we actually, the photographs that we take, I guess, they're not really, it's not optical wavelengths we're recording. We're actually recording infrared light, the energy that we receive from the infrared light. So as it allows you to take a picture of space objects as opposed to direct observation. I guess I'm not really clear on the question. Can you rephrase that question?
I'm guessing that Philippe means that taking an image and then later looking at it as opposed to looking in real time.
I see.
That's my guess.
So they do have a visual, like we said, you saw in the light path, there's a visual pathway. So they do get a visual picture, but the infrared light, that they receive, they analyze and process that data, so they know how much energy that light wave that they get from it is for the different wavelengths, and then they process that data to create the image. I hope that makes sense.
Mhm.
Yeah.
I was wondering if adaptive optics are used, as they sometimes are on ground-based scopes, where there's still a little bit of air atmosphere above the plane, and there's a lot of turbulence around it. So I wondered if adaptive optics are used on the scope.
I do know that they do a process called chopping, which is a similar idea where they use their visual. This is my best recollection now from 4 years ago. The explanation that was given to me is that I'm not sure I can call it exactly adaptive optics, but I do know that they do this process called chopping, where they look at the visual image and they have a sort of a baseline about what the ambient infrared light is, and then they subtract that off from the data they collect off of the infrared filter. I hope that makes sense.
Thank you.
Thank you. How often does Sofia fly? The idea is that they have, their goal was to have at least, I'm not sure. I know that they've used to fly at least 20 times in the fall season. When I was supposed to fly, they had like all these flights. They would have weeks of flying time. So, they would deploy to the southern hemisphere when they wanted to observe certain objects. They also observed Pluto. I can't come up with the exact number, but I know that it wasn't just like 4 or 5 flights a year. They wanted to get at least 20 teachers a year going through on Sofia. And if we all get about 2 flights, that's at least 40 flights a year. Yes, that's a great question. Is Sofia elevation higher than commercial flights? Yes, your commercial airliners, you're usually flying anywhere from about 31,000 to 37,000, sometimes 38,000 feet. Sofia flies significantly higher than that, between 43 and 45,000 feet. Again, it just depends on where the tropopause is, which is the boundary between the troposphere and the stratosphere. And there's actually an atmospheric physicist in the pre-briefing before we go on the flight. The atmospheric physicist that's part of Sofia says this is what our temperature and pressure readings are. This is where we see the stratosphere begins, and that's where we're going to be flying. And so there's someone that's in charge of figuring out exactly what altitude you're going to be flying. So my very first flight was 45,000 feet, and that last flight I shared with you, that's why it was lower, because it was my very first flight was in June. That most recent flight was in September. And so you know that the temperature and pressure is different from June to September. So that's why it changed.
$45,000 feet is about 8.5 miles or 14 kilometers.
Thank you. Just impressing upon my students why it's important to be able to convert between units.
I can do them in my head if no one's watching.
Any other questions?
Well, we're about at top of the hour.
All right. Well, thank you so much for having me. This was it. I always love talking about Sofia. If I know there were some questions that I felt like I'm not an expert in answering, but I'm going to type in the chat window here for everyone. Those of you who are on the Zoom meeting, it's sophia.us. Sophia.usra.edu. Let me just double check that. I'm going to paste the link to their Sofia website here, and then you can go find out a lot more. So those of you who are in the chat, anybody else who's like in the live stream, if you just Google Sofia Science Center, it's going to take you straight to their website, and you can learn a lot more about the science involved. There's links to the engineering involved in operating the observatory. And I'm hopeful that it has information about being an airborne ambassador. I did see someone ask about how to apply, and then Julia Candia, I will copy your email address and respond to you offline later. But it was so great to share with you, and as a plane flies above me right now.
Yeah.
It's
Thank
not
you.
Sofia.
This
Yes,
is the first
thank you
time
so
we've ever had a talk on Sofia, and it was absolutely delightful to have you. I know you talked to the San Jose group a year or two ago, and that's where I found you and this wonderful talk. Thank you so much.
Thank you for reaching out. It was such a
Yeah.
pleasure. You guys have a wonderful evening.
Thank you.
Thanks
Thank
very
you,
much for
Marita.
joining us.
Thank you.
Thank you,
Bye
Marita.
bye.
Bye-bye.
Thank you. Bye.